So are you done with reading? So I think this abstract is quite easy to follow and quite straightforward.
Well, because you're expert of transfer entropy.
Maybe. But at least there's some clear some motivation and gap sentence here. Yeah. And any other opinion about this abstract?
It's first time that I see someone saying I propose instead of we propose.
Oh yeah.
Because this
Yeah.
is a single.
Right. You'll need.
Oh, still say we,
Yeah, but
single author, still the royal we.
yeah. So anyway, Julia and Lee will be this May K-Science tutorials.
Right. Then let's start. Actually, maybe the first part of this talk would be we'll deal with the basics of information theory. So let's start with very basic things. So let's think about like this event. So the sunrise from and then east side, right? How would be the probability of this? One, maybe, yeah, it's almost one, but there could be some probability there. The other thing happens. So maybe we can also think about the probability that the sun rises in the west side.
What do you mean? In Canada, it rises in the west.
Oh, okay. Yeah, there could be other things, but yeah, that's because of distance. Yeah.
He's fake.
Okay, and yeah, maybe possibly the probability would be much lower, but let's just say that the probability of sunrise in the west is 0.0001. Then for each event, we can put minus log to this probability. And this value is called the self-information. And this quantifies how surprising or informative that this event is. You can see that this value, so self-information of sunrise in the east is very low. That means it is not surprising or not informative. So, and on the other hand, if you quantify the information of sunrise in the west, you will see that this is very surprising. So the self-information value is really large. Yeah. So this low value means this is not surprising, and this high value means, and this is surprising. This is the self-information. It quantifies how this event is surprising or informative. And maybe we can consider the random variable of this sunrise direction. Then we can calculate the average, the surprisingness or information about this random variable. This would be the probability of this multiplied by this information and some all of them events. Then the value would be this. And yeah, this value is called entropy, and it quantifies some average surprisingness or information. You can see that this average surprisingness is very low. That means, yeah, actually for this event, the average surprisingness we can get is not so high. And actually, so if we consider this kind of binary variable, maybe we can think of the probability of the plus sign comes and from the minus sign comes. Then you can, and this value represent the entropy value. And you may see that the entropy value takes the maximum value when the probability is half and half. You may think in this way. So if we already know that that the probability of plus is 1, then we already know that the value would be plus. Then there's no information we can get that even we observe that variable. So the average information is 0. But if it is, the probability is half and half, then maybe we need to observe it to be sure that this value is plus or minus. That's why there is a very high information we can get by observing this event. Yeah, this is basic of the self-information and entropy. Then we can also think about this kind of value called mutual information. This quantifies the kind of shared information between two variables. So this is summation of information we can get, the average information we can get by observing X plus the information from Y, but we subtract the information we can get only when we observe both of them. Then the meaning of this value would be the information we can get just observing either of them. So mutual information has that kind of meaning. And then if we just write down the equation for each information here, then the equation would be like this. So let's consider this simple example to get more intuition about this mutual information. So let's consider x and y, and this x and y can have a value of 0 or 1. And the probability would be, or all event is 1 over 4. That means the two variables are independent, half and half. Then if we calculate the mutual information, maybe we can use this equation to calculate the mutual information. Then, okay, let's consider this x equal to 0 and y equal to 0 event. Then the probability of this joint probability would be 1 over 4. But for the probability of x is 0 is 1/2. So here is 1/2. And at the same time, probability of y is equal to 0 is 1/2. Then this value would be actually 1. This value is 0. And we can calculate all of them and have the weighted sum to calculate this. And this would be 0. That means because they are independent, there's no information they are sharing. Then let's consider then this situation. So this means that when y is, so the probability of x is equal to 0, y equal to 0 is 0. But x is 1 and y equal to 0 is 1/2, like this. And if we calculate the mutual information here is, so if you do the calculation here, we will see that the value will be 1. So that means if we only, so let's assume that we only observe x, then the information we can get about y is 1. But y is 0 and 1, 1 bit. So that means we can perfectly know what would be y.
If we know the x.
And that's so natural because if we know that x equals 1, we definitely know that y equals 0. And also if we know x equals to 0, we know that y will be 1. So that's it. So that's the information we're sharing. So high mutual information means that they have some association or they have some relationship. And low mutual information or 0 means they are almost independent. They have no relationship. And also there's also another interpretation we can have here. So if you see this value would be different from 1 if this p, the joint probability is not the product of these two. If they are the same, you can definitely see that mutual information is 1. So maybe we can interpret this as it quantifies how the joint probability of between x and y deviates from what when the variables are independent. Yeah, this is the mutual information. And also we can consider more things about this mutual information, which is called the sorry, I missed this. So, and also we learned the concept of entropy before, right? So maybe we can rewrite this mutual information with the terms of entropy. And we know that the entropy is the average surprisingness or uncertainty of this each variable. And also we can think about some conditional entropy, which considers the value of the conditional probability, that the information we can get from this conditional probability. Then we can see that this corresponds to this, and this value corresponds to this. Then we can write mi as the entropy of x minus entropy of x conditioned on y. So that is, that means we can say that this also can be interpreted as the visual information. And also, yes.
Initial entropy, average uncertainty. Okay.
Isn't there like a bias sign out of place here?
Oh, did I miss something? Oh, I think
It just seems like the h of x is the wrong
I
sign.
missed something here. Minus sign.
No, yeah, it's just a minus sign, I think.
Okay,
Minus
yeah.
minus sign.
So we need to again minus sign here, and then
Right?
oh yeah, this is right.
So,
Yeah, this is
so anyway, the final conclusion will be mutual information equal to uncertainty of x minus conditional uncertainty of x given
y.
y.
Okay, but then you need to put a minus sign on your h of x then.
Minus sign here.
Yeah.
So the sign of I y is gotta be the sign, same as the sign of I x, because it's in the denominator up there.
Oh, no.
I think this is right.
That's right, because if we subtract
Oh,
the bottom,
yeah,
then
Yeah, right.
yes.
There's a minus sign, right?
That's right.
Good.
Yeah, so this is
I think that's the key concept we have to know, right?
right.
So mutual information between two variables is one variable's uncertainty minus one variable uncertainty for given another variable. That's that we call mutual information.
Yes.
If x and y are independent, then conditional uncertainty, original uncertainty should be no differences, so that
Right.
mutual information should be 0. Okay.
So that's the mutual information. And there's another concept related to this mutual information, which is the conditional mutual information. So this is the situation where we have three variables,
Okay.
x, y, and z. And the concept is simple. We just put conditioning z for all of them. Then we can calculate It's the same way as we did before. And let's see one example to get more intuition about this conditional mutual information. So here, again, x, y, z can have value either 0 or 1, and p, x, comma, x, y, z is 1, 4, 3. Then, actually, if we calculate the mutual information, the condition on Z here, for this event, the probability of this one, condition Z, x equals 0 and y equals 0 is actually 1/2. Condition on only this 4 cases. And here the probability of p x is equal to 0, condition on z equal to 0 is actually x can have 0 or 1, right? So it's also 1/2. And also when z is equal to 0, the probability of that y is equal to 0 and y is equal to 1 is also 1/2. So, and we can do same calculation for each cases. The resulting conditional mutual information is 1. That means condition on Z, we can know Y even if we know only X. That means that even, so consider, so only these 4 cases, okay. When Z is equal to 0, if we know that X equal to 0, we know Y is also equal to 0.
Probably.
There's no probability here.
Okay, gotcha.
And if Z is equal to 1, then we know that when X is 0, Y is always 1.
Oh.
So the only condition on Z, we know that X, we only from X, we know everything about Y. That's the meaning of this conditional mutual information. And this is the meaning. And interesting part is that if we do not condition on Z, actually the mutual information between X and Y is actually 0. Because it is the same case of this case. So mutual information is 0. So that means the mutual information between X and Y is actually 0, but by knowing Z, there is an information that X and Y variable shares. Alright, this is the conditional mutual information. And this mutual information is the quantification of information between some kind of static random variables. But actually there can be some time series data. And we can also quantify the information shared between these 2 time series. This is called transfer entropy. Transfer entropy itself can be written as the conditional mutual information, like this. The information shared by the previous history of X and current value of Y, conditioned on previous history of Y. So maybe there could be some lags or some memories can affect the current value, but to simplify it, let's assume that L is just 1. Then maybe we can draw in this way. So this is we can say that the transfer entropy is the information shared between xt and yt plus 1, conditioned on previous history yt. Or also we can rewrite this as the entropy term, which is the entropy or uncertainty of xt plus 1 condition on this previous history, but how much the uncertainty decreases by knowing the previous history of x. So that means even if we know the previous history of y, how much information we can get from previous history of X about the current value of Y. Yeah, maybe we can interpret it this way, and some key properties of transfer entropy is that the higher value means that there's more information we can get from by knowing the value of X about Y. And also transfer entropy, entropy is actually the mutual information. So it is always positive or non-negative, and it's also a directional measure. We can calculate transfer entropy from X to Y, and then also we can measure the transfer entropy Y to X. And at the same time, we can also consider some conditional transfer entropy, which is the same. There's another third variable Z, and then we can calculate the mutual information condition on Z possible. So there's also transfer entropy we can calculate, condition on Z. And these measures, and including the transfer entropy or condition transfer entropy, are widely used to observe for causal relationships. And let's see some example to calculate how to calculate this transfer entropy. Right. So there's two time series, X and Y. And X both can have a value of 0 or 1. And there's a time series. And let's just assume that's a Markovian, which is, we only consider the very previous history. Then we need to calculate this transfer entropy, we need to calculate the conditional entropy, right? To do that, we need to calculate the conditional probabilities. Okay, let's see one by one. So we need to quantify this. Then we need to calculate the conditional probability that P when the previous history is 1, the next history should be 1. There are two cases for that, and condition on that yt minus 1 is equal to 1. Also, there are two cases that the yt is 0. So the whole cases are 4, and for these cases we have two cases, and for these cases we have also two cases. So the conditional probability is 0.5, and 0.5. And in the same manner, we can also calculate the condition on that yt minus 1 is equal to 0. We can count the cases, how many cases that yt is equal to 1. So, for example, there are 2 cases. And also, when this is 0, only the one case is that yt is equal to 0. So, the conditional probability is 2 over 3, and the last one is 1 over 3. Then we can calculate this entropy in this way. So, there are these paired cases, the whole cases are total 7 cases, right? And among these 7 cases, 2 cases correspond to this case. So the probability is 2 over 7. And then we multiply this information that we can get. And with the sum, then the final output is 0.965. This is this entropy value.
I mean, it's about again, it's uncertainty, right?
Yeah, uncertainty. Not mutual information, right? Uncertainty.
If we know the previous yt minus 1, the yt uncertainty is about
But we don't know anything. It's almost like this.
So if we have really no idea, then what would be the maximum uncertainty?
It'll be 1.
1.
Yeah.
In this case, we have little information.
Then we can also calculate this, how much uncertainty is decreased by knowing the previous value of x. To do that, we need to consider this conditional probabilities. Yt minus 1 is equal to 1, xt minus 1 is equal to 1, something like that. Then, but if you calculate all these cases, you will see that all values are 0 or 1.
So uncertainty is 0.
Uncertainty, yeah. This is 0. So actually the transfer entropy is quite large.
This is how much we gain, right?
Right. That means, yeah, if we know previous x value, we can pretty sure what will be the future value.
Both x and y.
Yeah. So this is how we can calculate the transfer entropy.
And then this indicates that as x affect the y.
Yeah, definitely there's a very much information we can get that x from x to y, and this also indicates there's a causal relationship from x to y.
So if I understand well, in that case, that means that because we have a large entropy, if we know x, we are pretty much sure that we can predict y.
Yeah,
Okay.
this indicates how much decreases uncertainty. Yeah, and this is actually for the cases where x and y are some discrete random variables, and also we need to consider some when variables are continuous values, and there are some approaches for this, but the simplest one would be change this continuous variable to discrete one by using some binning method. So, for example, if we have this kind of trajectory here, we use two bins. Then if value corresponds here, we maybe assign value 1 here, and if value corresponds here, assign value 0 here. And then this continuous variable b, change it to discrete variable time series with two values. So in this way, we can calculate transfer entropy. Or another way is we just infer this joint probability. Maybe we can assume that the random variables there maybe follow some Gaussian distribution, multivariate. In this way, we can just infer their parameters and also calculate the conditional probabilities and eventually calculate the transfer entropy. This is the regular way to calculate transfer entropy. And another thing we can do with this transfer entropy is draw the graph from the network. For example, let's think we have 5 variables, 1 to 5. Then each variable will have this kind of time series or this kind of time series. And for each pair, we can calculate the transfer entropy, and then we can maybe statistically test whether this value is high enough. Then if set is significantly large, then we can connect two nodes. Yeah, maybe if indeed very large, statistically large, then we can draw the line connecting 1 and 5. And actually this statistical test should be done in this way. So theoretically, if the positive transfer entropy always means there's some information sharing or information going, but because the time series is finite, the estimated transfer entropy value can be positive even if they are independent. So
Because luckily,
accidentally, that kind of thing happens. So
if the time series is extremely long, then we are fine. But in our lab, we never get such extremely long enough data.
Right.
They always provide short data sets so that even their independent transfer entropy can be accidentally greater than 0.
So to do that, we will calculate some null distribution of the transfer entropy values, assuming that there's no relationship between x and y. For that, we can take this approach. So we first calculate the transfer entropy from the original 2 time series, and then we just mix the order of the source variable randomly. Then there should be the relationship between x and y will be gone because we randomly shuffled it. And for the shuffled one, we can also calculate the transfer entropy. And the value would be, maybe we can think that that transfer entropy value is the transfer entropy sampled from the 2 time series that doesn't have any relationship. So if we do multiple times for this one, we can eventually discuss a null distribution. And we can also consider this original transfer entropy. If transfer entropy value is high enough, maybe the high 5%, then we can say that the p-value is 0.05. Then if that holds, maybe we can say that, okay, this transfer entropy value is statistically significantly large.
So, and here, when we perform the surrogate test, we randomly mix the x times series.
Yeah, right.
So, and actually, we also use it for the Gobi as well. But Oli, please study that paper. Maybe if it's good, maybe you can do for journal club. Because I gave a talk a couple days ago at the Busan at the IBS Physics, Climate Physics Center. And then I talk about surrogate test, but the director said he's worried about this random surrogate test. So that he suggests a better one. It's called Tyler surrogate test. So Oli will study and teach you.
Oh, okay. Right. So in this way, we can test the kind of causality between 2 nodes. Then eventually we can, for example, we can draw like the graph like this. So 1, 2, 2, maybe 2 to 5. But this should be directional because transfer entropy is the directional measure.
Causality.
Yeah. And then for this graph, we can measure some degree of each node. So maybe out degree. Then the out degree of 1 is 1, and 2 is 3, like that. This one, this one. And then with this degree, maybe we can conclude like this. The key component of this network is 2, because it has the largest out degree. You can also maybe interpret that it is most influential variable. So this is kind of the traditional approach. And also we can consider this in degree, and in that case, the 4 has the largest in degree. Then maybe the component 4 is the most influenced variable, like that. But actually this approach looks quite naive because we only consider the degree. We don't care about how much information that this variable can provide to others. We just consider this binary relationship. So the author said that, oh, this has a limitation.
Okay.
So yeah, this approach disregards the actual transfer entropy. And also, maybe we can think about some weighted edges with transfer entropy value, but actually transfer entropy value itself is not additive.
Additive.
Yeah, so it's not so reasonable to consider that kind of things.
I see. Because we can add a t value for each arrow, and then we can just add it sometime.
Yeah,
But that's too naive.
Yeah, too naive. So that's the limitation that the author said. So to overcome this limitation, he suggested this out or int. This is actually not so different one. So we consider x to the whole variable's joint distribution. So, for example, we previously only considered the only pair of 2 variables, but let's consider these 4 variables is a just vector random variable.
Vector?
The vector random variable. So we can consider the joint distribution of these two variables.
Okay.
Then, this is y vector here. And then we calculate the transfer entropy between x and y.
But 2, 3, 4, 5 was originally has a vector, right?
Time series. The time series of vectors.
Vector. Oh, I see. So
Yeah.
it's matrix. We can.
Yeah, matrix, yeah, right. Then we can calculate this, the transfer entropy from x to the whole rest, and also transfer entropy from whole rest to x.
So, can we calculate the once?
Let me
You do it.
example. Yeah,
Oh,
example.
sure,
Yeah.
okay.
So it's like this. So we have this 3 time series here, and we want to calculate the RT of xy. That means we will consider how much information from x1 to this vector valued random variable 2, 3. And to do that, we need to first calculate this entropy. Then we need to calculate the conditional probability of this x2 and x3, this paired random variable, conditional on previous time. Then, so the first application, I just said that these two values are the same. Anyway, we can calculate the conditioned one that the previous is 1, 1. We can count the cases. The next is 1, 1. And also, next is 0, 0. If we calculate if you count the cases, we can get the condition variable probably like this, and also we can calculate like this. Then the entropy will be like will have this value. And at the same time, we can also consider we can add the x1 here, condition on x1 equal to 0. So in the same manner, we can calculate the conditional probably like this, and we can eventually calculate this, the entropy like this. And then we subtract it, we can get this transfer entropy from x1 to rest of them. This is the RT value. And in T value is also can be calculated in the same manner.
So in T means 2, 3 to the.
Yeah, 2, 3, 2.
If we know the 2, 3, how much?
Yeah, right. So this is more reasonable because this quantifies how this single variable can give information about the whole variables. So the author thought that this is more reasonable measure to quantify maybe the key player of the network. But actually, if the system size is very large, this the transfer entropy estimation can have significant edge. And let's see why that can happen. So let's consider this simple network here. There's only one relationship between S and R, which is RT is determined by previous S and R value. And the C1 and the C1 to Cn variables are just independent random time series. Then in this case, the transfer entropy from S to R is equal to 1. So if we calculate the RT of S, that value should be 1 because there's no information we can get about this, just random independent variables. But, so this is one example time series we can get. And if we calculate the RT for this case, actually the whole condition probability is just 1 or 0. That means this entropy, the estimated entropy value is 0. And then because this is the maximum value of this transfer entropy. So that means this transfer entropy value is also 0. So even the true value is 1, for this sample time series, the value is always, the value is 0. So highly underestimated. Because this space is too high dimensional, and if time series is too short, it's too sparse. So yeah, this calculation, so we need to take a log of these values, but we have only observed only single cases,
Event, I see.
then almost all values would be 0. So that's why we usually underestimate this transfer entropy.
I see. If we consider many variables as a condition, then we need to calculate again joint distribution of
Right.
many variables. Joint distribution of many variables require many data.
Right. If it's sparse, we tend to estimate that the entropy is equal to 0. So
If there's many variables and a whole bunch of them are independent, meaning they're spread out, their samples are spread out. But if they were highly correlated,
But even sometimes very highly correlated, that means
maybe
they're focusing on some zone, but other part will never appear.
yeah. So even that highly correlated, then maybe the sample should be
You have
only should. Oh yeah. So maybe highly correlated, the joint distribution would be like this. But even the time is not long enough, we only reach single point of this. Yeah, but even in that cases, if you calculate the conditional probability of each cases, it would be 1 or 0. And eventually the entropy value would be just 0. So we need some enough samples to cover this whole, maybe the whole the support of this joint probability. That's the key point. And similar thing happens for the int. So this is another example of this time series. And if we calculate the int s should be equal to this transfer entropy from R to S, but it is 0 because S is just randomly chosen, but only R is deterministically chosen by previous S and R. But if we calculate this, we need to calculate this in T, then we need to first calculate the entropy value of this ST itself, ST and ST minus 1. Actually, but the dimension is not high for this one. So this value will not be 0. So we will eventually get this quite high value. But, but when you try to calculate this one, because again the dimension is too high, too sparse, and then the final value would be 0. That means this value would be very high. Yeah, because this dimension is not high, so its value would be pretty accurate. But this estimation would be very inaccurate. It would be very close to 0. So that's why. So for this case, the transfer entropy is overestimated. Yeah. So int and out has two different trends of estimation adding. So he made this random samples like this, and here x-axis means the length of time series, and this graph value means the estimated out value and int value. So let's ignore this time series and just consider black, blue, and green. You can see that when there is no n, that means no c, only two variables, then the estimation is quite accurate. It should be equal to 1. It should be equal to 0. It's quite accurate. But as the number of c increases, this should be 1, but you can see that highly underestimated.
I see.
And even we have so many tensors, it does not be close to this 1 value. So this estimation error is quite significant.
Okay, gotcha.
Yeah, that's the key problem of this out t and in t. So the key idea of the author is using some pruning. So originally we need to calculate these entropies about this very high dimension, but not doing this directly. But we first calculate this network here. We can do the previous approach. We calculate the transfer entropy between each pairs and connect them. Then, based on this, let's see this one. Only 2 is connected with 1. That means we don't need to care about the other variables. So, in y, we just remove except 2. Because they already does not have any causal relationship between 1 and others, except 2. And then we calculate our t. So it's kind of dimension reduction, or yeah. So originally this y should contain whole other variables, but we do this pairwise thing first, and then if there is no connection from 1, then we just remove all of them from y.
So when we don't have any outgoing edges, then we don't have to calculate out t.
Right, we don't need to. But actually, this, I think this is also a kind of estimation approach.
But
Not
in a way, we don't need. Okay, we use, for instance, from two other variables, then we will consider 3, 4, 5.
Yes. Still, yeah, that's the key limitation of this approach. If there are so many connections still, then the estimation could be also inaccurate. But then I think this is the best thing. The simplest, yeah.
I don't remember why we care about in t
And out t rather than this pairwise.
Yeah.
Can you explain?
Oh yeah. So in the pairwise one is the key player is determined only by this degree. We don't care about how much information it can give, but how much variables are connected.
So, for instance, if we only look at the pairwise just graph, the most powerful one looks like 2 because 2 has a 3 outgoing arrow. But if these 3 outgoing arrows are all very small ones, very small transfer entropy, then maybe even though 5 to 4 is only 1 arrow, if 5 to 4 is very strong, then rank could be changed. So he want to, I think, quantify the power of each node in terms of transfer quantity. So that's why he decided using the outgoing transfer entropy. That is basically total outgoing transfer entropy, but calculation is too challenging.
Right, exactly.
I see.
So yeah, maybe this pruning approach is the very simple remedy for this problem, but there could be also some rooms for achieve more better approach to accurately estimate this.
The pairwise method is good at getting the graph, the directed graph.
Right.
And then once you have the directed graph, that gives you a better way of looking at interactions that are beyond pairwise.
Right, and based on that, we only just cut some variables. So when you consider the relationship, we only focus on more powerful candidates. So that's the idea of this approach.
Is it is it possible to have cycles in the resulting graph from the pairwise test?
Oh, yes, I think so, but it's because always, I heard that when you consider some causality things, the cycle always causes some problem. Yeah,
Okay.
maybe if we consider more delays, that can happen a lot. Because with some
And it's like
connected
picking your
ones,
principal component cutoff.
just
How far, how many, what's the delay? What delay do you pick?
Yeah,
You can pick any delay you want as an answer.
So I have a question. When you calculate this out TP, so we have to consider all the nodes, or can we consider all the neighbors?
Oh yeah, this is the way. So originally, we should consider 4 variables, but this approach is considering only the neighbors. So the neighbors is only directly connected. Yeah. So yeah, so with the same example, yeah, the other is red and orange. The others represent the estimated value with prune. So because they are all independent, I think most of them are excluded from the neighbor. Then they could get much more accurate estimation of this transfer entropy value.
I see.
So it should be close to 1, and you can see that the pruned one is almost accurate, even with this high M value.
I see.
Yeah, that was the idea. And
So here by pruning,
Mm.
for instance, from the 6 variable, how many variables are killed?
oh, he didn't explain. But as you can see, if the time series is not so long, even
Oh, yeah, of
we
course,
use
of
pruning,
course,
this can
of
be.
course, yeah.
Yeah.
That's fine, yeah. But if pruning killed the like 5 variable, then it's just pairwise, right?
Yeah, but I think that's why this can happen. This, yeah.
See, okay.
So this is so testing of this approach for the some kind of simulated data, and they also applied this approach for the real data. So from this paper, they obtained some microbiota data on daily timescale. So data obtained from the liver sample and over 200 days, and the variable number is 879. So when I saw this paper, this is the time series we can get from data. So this color means each variable, and this time series. So I think it's my first time seeing this kind of time series. This color means the level. So this blue means the low value, and this orange and red value represent the high value. And each one is for each variable. I think actually there are more than 300 time series, but I think because to calculate the transfer entropy, the time series, the stochastic dynamic should be some static. So maybe this kind of special event cases could be excluded to calculate this transfer entropy. That's why they use almost 200 variables. But unfortunately, in the paper, the author didn't explain well how they applied this one. Yeah, but anyway, we can apply the transfer entropy approach here. And yeah, we calculate this LT for each variable. And this is just ordered as with this estimated values. And we can see that without pruning, almost all cases, the calculated RT value is equal to 0. It's highly underestimated. The 800 variables cannot be very accurate. And also in T value, with pruning, the maximum value is actually near 0.5. But without pruning, you can see that very high value is also observed. So maybe this represents some inaccurate estimation. And interesting is that, so they found some two key variables or two key species which has the highest RT value. And they said they found some literatures and said that these two are indeed very critical key player in this network. And also they mentioned that the in T value is a little bit doubtful, so they didn't found any some key players here, and also its interpretation is also I think it's difficult because what would be the most influenced species from the network? Is it really critical? Maybe it's not. But anyway, using this RT approach, they indeed identified the key players of the network. And also, when you apply this the conventional approach, which only considers the degree of the each node, they couldn't find any two key players. Yeah, this is the key point. So actually, this is the drawn network graph. These the two key players didn't have any pathways, but the information, the quantity of the value of information is quite large.
So TF output in TF is very high, but degree is not that high.
Now degree is not high. So maybe these variables
Looks like half.
yeah, looks like hot, but their information is not so high, and maybe they are not the key player of the network.
Or maybe it could be
Yeah, we-
underestimated.
Huh? Yeah, I also agree with that, but yeah, anyway,
if you have a high degree,
yeah,
the chance of underestimation is
Higher.
higher, right? So, but I'm not sure whether it is really critical component in this network, but the other didn't mention.
You could test this with synthetic data, right? You have a bigger network like this,
Yeah.
some nodes with a lot, just in this sort of situation.
Yeah, we can try. Yeah, this is the last result, and the summary is that we studied these some concepts, key concepts in the information theory, and especially the transfer entropy, and the author introduced these two, LT and INT, that high dimension or short time series can cause some significant transfer entropy estimation errors, so maybe using pruning, we can reduce the dimensionality. Yeah, thanks for listening.
Thank you. So yeah, any question?
So using that method, basically we can identify key players in a network.
Mhm.
But is it possible that sometimes in a network we don't have we have some kind of group of key players? Like let's say for example you have a set of data per patient or a cancer patients. You have their age, how many cigarettes they smoke, how much alcohol they drink, and what biomarkers value. So let's say, for example, just age itself is informative, but not so much. But if you combine age with the quantity of alcohol and numbers of cigarettes, then you get a very powerful predictor. And each variable is not powerful on their own, but as a group, they are very powerful predictors or key players. Does this method can do that? Because it seems that we can just only detect whether it's node 1 with the rest and not node 1 and 2 versus the rest.
Maybe we can think about the definition of transfer entropy. So maybe you mean there's a variable x and there's another variable x1, x2, y. And what you mean that maybe not a single one, but the interaction between x and something else can also give some good information. That's the point.
Maybe more information, but
Yeah.
if you take one.
But yeah, the transfer entropy is mutual information that x t minus 1 and the whole y t minus 1. So there are y t conditioned on y t minus 1. That means we also consider condition on this one. So their interaction is also considered in transfer entropy calculation.
Okay, so the answer is yes and please.
Yeah.
Thank you.
But you could have, I mean, what's the example, like a mass relationship? Maybe I don't understand the answer that you just gave yet. But the influence of y1 on x and y2 on x individually are negligible. But when you condition on both of them together, you see a strong correlation.
Yes.
I don't see, yeah. So when you make your directed graph, you're only looking at pairwise interactions.
In the graph, yes, right.
So you might not have an arrow from y1 and y2 to x, even though both of them together influence x.
Yeah, but this is our t, not directed graph. Yeah, our t case we.
No, because I'm talking about in the pruning strategy,
Okay.
right? 'Cause you
yeah.
know the graph.
Yeah, that's right. Yeah, if we apply pruning, maybe we miss that information.
So maybe you want an error, you wanna have a low threshold for your directed graph, but then you have a lot of edges, you're not pruning very much. So then you probably have like a delicate balance that you have to strike. So if you do better than just pairwise, you build your graph from three-way comparisons. But that's computationally more,
Yeah.
at least you have dimensionality problems, but not, it's controllable. You need longer time series than pairwise.
Yeah. Actually, yeah, this I also read that this approaches has a lot of limitations. Yeah. Maybe there are also some controllable parts, but anyway, if there's not many data, yeah, I think this method is not so useful.
Did they provide any comparison study with the conventional transfer? So if you use the conventional method, you can draw the graph and you can obtain the connecting weight for the edges.
And then sum them. Sum all the.
Summation. Actually, it is included in the paper, but they just tested this. So two key players. The previous approach didn't find these two key players.
Even we sum them.
Yeah, even we saw them.
Okay, any other question? Yeah, I know bright sun make you sleepy, right? Well, your circadian rhythm is a little longer. Okay, so then let's thank the Yunmin.